Welcome to The Explainer. I'm absolutely thrilled you're here today because we're going to explore a force that is literally constantly pushing against us, yet we rarely give it a second thought. We are diving deep into the extreme limits of human physiology and looking at exactly what happens when we journey far, far outside our comfortable one-atmosphere bubble.
Think about it for a second. Right now, you are sitting at the very bottom of an ocean of air. It's pressing on you from all sides, literally holding your biology together. But what happens to your body when that invisible weight is completely stripped away? It's a slightly morbid thought, I know, but it is absolutely crucial to understanding our incredibly comfortable existence.
So let's kick things off by heading beyond the blue sky and ascending the atmosphere. Before we get too high up, though, let me ask you a quick question. If you could snap your fingers right now and make the Earth's atmosphere just disappear, what would the sky look like? Take a second to really picture what you'd see when you look up.
Well, the very air that gives us life and maintains our body's pressure is actually what paints our sky blue. It's a phenomenon called Rayleigh scattering. Basically, the shorter blue wavelengths of sunlight get scattered all over the place by the molecules in our atmosphere. Without this scattering medium, we wouldn't see blue at all. We'd be staring directly into a pitch-black abyss, which is exactly what astronauts see in space.
Okay, moving on to our next phase, ascending the death zone and braving extreme altitudes.
As we climb higher and that barometric pressure drops, our bodies really scramble to adapt to the lack of oxygen. First thing, your sympathetic nervous system kicks into overdrive. Your resting minute ventilation shoots way up, you start hyperventilating because of your hypoxic drive, which ironically drops the carbon dioxide levels in your blood. Then you get tachycardia, meaning your heart rate and cardiac output spike to compensate. Go high enough without acclimatizing and you're facing decreased cognitive function and even sudden delirium.
But consider this incredibly staggering number, 30 millimeters of mercury. This wildly low alveolar oxygen level was actually survived by a team of healthy, fully acclimatized mountaineers right at the summit of Mount Everest. To put that into perspective for you, down here at sea level, that number is over 100. It's just a crazy testament to the incredible, albeit somewhat fragile, adaptability of the human body.
Now let's push even higher up to the Armstrong limit and talk about the boiling point. Up at 63,000 feet, we cross a genuinely terrifying physiological threshold known as ebullition. Because there isn't enough atmospheric pressure holding your liquids together at this height, you get a net conversion of liquid to gas, meaning water vapor bubbles literally start forming inside your bodily fluids. This expands your tissue volume incredibly rapidly. Thankfully, the vapor pressure usually isn't strong enough to actually rupture human skin, but that's entirely due to our tissue's natural elasticity.
So what does this actually mean for the fluids inside you? Well, as environmental pressure drops, the temperature required to boil water drops right along with it. Once you cross that 63,000-foot threshold, the famous Armstrong limit, the boiling point of water drops to exactly 37 degrees Celsius. And you guessed it, that is normal human body temperature. Above this line, the fluids in your body can literally boil just from your own body heat alone. No way, right?
To see what this looks like in a real-world survival scenario, let's look at the incredible case of Joseph Kittinger back in 1960. While he was ascending in a helium balloon gondola to the very edge of space, his right-hand glove failed to pressurize. Because of that localized ebullition we just talked about, his hands swelled up to roughly twice its normal volume, bringing on some seriously disabling pain. Even after he safely returned to lower altitudes, it took a full 3 hours for his hand to finally deflate back to normal.
Let's take it all the way to the edge now, surviving the vacuum and zero pressure.
If a spacesuit or cabin seal breaks, things happen frantically fast. At 0 seconds, decompression occurs. The expanding gas in your chest pushes hard on the mediastinum, and this triggers a vagal reflex that forcefully drops your heart rate. Your oxygen completely plummets. Within just 12 to 15 seconds, you hit the absolute end of your time of useful consciousness, and you pass out. It is a terrifyingly fast countdown. But amazingly, survival is possible if the response is immediate. Get this, in 1968, a technician accidentally disconnected his umbilical hose while inside a vacuum chamber. He lost consciousness right in that critical 12 to 15 second window. Fortunately, the chamber was rapidly recompressed. He woke up shortly after, and surprisingly, he had absolutely no memory of any chest or abdominal pain. That immediate recompression literally saved his life.
And, human biology can sometimes protect itself in the absolute most bizarre ways. During the Space Shuttle STS-37 mission, a metal bar actually punctured an astronaut's glove while he was out in the vacuum of space. He didn't even notice at the time because he was so pumped full of adrenaline. So what saved him? Well, he bled into space, and his coagulating blood instantly sealed the tiny opening right around the bar, creating a temporary biological patch against the vacuum of space. How crazy is that?
But we also have to somberly recognize the absolute limits of human survival here. In the tragic Soyuz 11 incident, a valve leaked during the crew's return back to Earth. The cabin depressurized to 0 millimeters of mercury over about 100 seconds. Voice tapes later showed the crew actually discovered the leak, but their time of useful consciousness was simply too short for them to fix it, which tragically proved fatal for all 3 cosmonauts.
Okay, so we've looked up. Now let's dive down into the crushing depths of hyperbaric environments. We've just seen one extreme, but what happens when we go the complete opposite way? Under hypobaric or low pressure, we face hypoxia, our blood boiling through ebullition and cardiac vapor lock. But when we plunge down and actually add pressure in a hyperbaric environment, a totally different set of biological nightmares begins. We're talking nitrogen narcosis, severe muscular tremors, and dyskinesia.
Let's take a closer look at nitrogen narcosis. Under high barometric pressure, normally harmless gases, like the nitrogen we literally breathe every single day, become highly toxic hazards. The increased pressure forces that gas to alter the physical properties of your nerve cell membranes. This results in some pretty debilitating muscular tremors, massive loss of coordination, severe memory deficits, intense confusion, and eventually deep psychosis.
Despite all these extreme hazards, humans have still managed to push the boundaries in this direction too. The record is held by a diver named Theo Mavrostamos, who actually survived a simulated depth equivalent to 70 atmospheres. That is 701 meters deep. At this absolutely crushing pressure, he suffered from profound fatigue, mild myoclonus tremors, and dyskinesia, but he managed to survive by breathing a highly customized helium-hydrogen mix.
But eventually, we reach the ultimate biochemical limits of life itself. Extreme pressure doesn't just disrupt your breathing, it literally dictates the laws of chemistry. Deep-sea fish manage to survive down there by producing a chemical called TMAO to hold their proteins together, but even that has a hard limit. At 5,000 atmospheres, the 3D structures of proteins just self-dismantle. And at 15,000 atmospheres, proteins completely unravel into individual amino acids. The pressure literally unzips the molecular building blocks of carbon-based life.
Which brings us right back home to exactly where we started. As you sit comfortably right now at exactly 1 atmosphere of pressure, do you feel that invisible weight resting on your shoulders? It's so easy to forget. But that perfectly balanced ocean of air is the literal only thing holding the physical and chemical reality of your existence together. Thank you so much for joining me on this explainer, and I hope you never look at the air around you the exact same way ever again.